Let's explore compressions and stretches. Let's start with a function given by a formula. The formula is f of x. We can then create a new function. We can consider the function given by the formula a times f of x. Here, a is a positive real number. Let's call this function g. So g has the formula g of x equals a times f of x. We can see them this way. Here's our function f. Here's our function g. And what happens to the input x? First, under the function f, the output of x is f of x. And then under the function g, the output of x is g of x, which is a times the output of x under f. So let's see whether there's a significant relationship between the graph of y equals f of x, the graph of the original function, and the graph of this new function. This is divided into the following three cases. Let's see how. First, when a equals 1, we find that g of x equals f of x. So the graphs are the same. The graph of this new function, y equals g of x, is the same as the graph of y equals f of x. What about when a is greater than 1? Let's do an example. Let's take the function defined by the formula x cubed. And what can be said about these two graphs? First, the graph of y equals f of x looks like this. What about the new graph? When the input is positive, what can be said about the two outputs? On one hand, you have x cubed, the output for f, and you have a times x cubed, the output for g. We see that x cubed is positive since x is, and a is positive. It's a positive number greater than 1. So this number on the right will be larger than the number on the left. Let's take a look at the graph of this new function for positive inputs. It looks like that. The graph is taller. What about for negative inputs? Well, when x is negative, so is x cubed. And I'm going to multiply this negative number by a positive number greater than 1. So ax cubed will be even more negative than x cubed. So this second output is smaller than the first output. And here is the rest of the graph of this new function. So we see that the new graph is taller. You also say the new graph is a vertical stretching of the original graph. What about when a is between 0 and 1? Let's look at the same example. When x is positive, both of these outputs are positive. And since a is less than 1, we see that the second output will be smaller. The second output is smaller than the first output. Now, when x is less than 0, when it's negative, the two outputs are negative as well. And since a is between 0 and 1, the second output will be less negative than the first. So we see that this is reflected in the graph of the new function. The new graph is shorter. It's shorter than the original graph. This is called a vertical compression.